All right, welcome back. The last video we used calculus to find the electric field at some point of interest caused by a ring of charge, right? A circular wire of charge, and it was, kind of right on that axis of symmetry. And we're going to do something similar now. The only difference is that instead of a circular wire of charge, we're going to go ahead and get into the area business, right? The area charge density business. And we're going to do a disk of charge with pretty much the same configuration, like we've got this axis of symmetry is where our point of interest is at. The distance that it is away is labeled A. This time, the total radius of the disk of charge is going to be called R. And of course, once again, we're going to go ahead and let sigma be constant. We're going to assume that we're given sigma, surface charge density of the disk, A, the distance from the center of the circle to the point of interest, and R, the total radius of the disk. All right, so tough part about this one is setting it up. And unlike the last problem, the integral isn't super easy like it was last time. It's not extremely difficult either, but it's definitely feels more like integrating. So you could pick out a little chunk of charge like this. You could pick out a dq and draw the radius, right, the distance it is from the point of interest. That's going to turn out to be a much more complicated way to solve this problem. And I believe, if I'm not mistaken, you would need a double integral for this problem. And being as double integration comes up in Calc 3 at CWI, for every problem I can imagine in this class, it's going to be able to be simplified into a single integral. So there's a clever way to do this, kind of using the result that we got in the last video, which is we figured out the electric field caused by a circular wire of charge. And so you could really imagine that what is a disk if not many circular wires of radius from 0 all the way up to big R, right? So you could just keep on stacking these things and you'll end up getting that disk you want. So let's go ahead and pick our dA, right? Our infinitesimal area. Let's pick it to be this band. I'm going to draw it a little bigger than it would be, right? Because it's supposed to be an infinitesimal, but I'm going to draw it a little bigger so it's easier to see. And let me even shade it in. So this band is going to have a certain area to it. We're going to call that dA. But first, I'm going to go ahead and say, okay, this band contains charge in it. And the amount of charge contained in this band is going to be called dq again. Okay. And then let me draw the band again a little bit off to the side so that it's easier to see what we're doing here. So this band is going to have a width of dy. So I'm still saying, this is the y direction, this is the x direction. Same configuration of coordinates as the last problem. And of course, each one of these bands is going to have a radius, which we're going to call y, right? Y is the measure from here to here. And then, of course, the width of the band is going to be dy. So that's pretty much the same thing I have drawn over here. And okay, so thinking back to like revolutions of solid in Calc 1, how I could find the area here. So, well, firstly, we know that dq can be rewritten as the surface charge density times dA. And that was from a few videos back when we talked about charge density. So now it's like, okay, we've passed the buck on from dq. That's going to be hard to integrate with. And so now we've passed the buck on to dA. And I'm not sure we want to do that either because, dA would be, it could be dx, dy, which would end up making us do a double integral. So that's why we picked this band here And we're going to integrate all such bands from radius 0 out to radius big R. So dA in this case is going to be 2 pi r, or I'm sorry, 2 pi y, right? Because the radius of the band is y. So that'll give you like the circumference, right? The circumference of this band. But then the circumference does have a little bit of a width to it, dy. So this is what makes it a surface, right? This is now a surface area that we're dealing with. So the infinitesimal area element is going to equal the circumference of the band times the width of the band, 2 pi y, and then dy. All right, so then we can go ahead and figure out, let's see here. So we know from the last problem that we found out that the X contribution to a, or the electric field contribution due to a circle of charged wire is equal to Coulomb's constant times A divided by A squared plus Y squared to the 3/2 times the total charge Q. And so in this case, we're not really interested in the total charge, we're interested in the little charge dq. So on both sides, we can go ahead and just say, and remember, the Y contributions all cancel out for every ring of charge, just like in the last problem. So really EX is just E in this case. It happens to point in the X direction. So putting a differential on both sides, we could say that DE equals KE times A divided by A squared plus Y squared to the 3/2 with respect to Q, right? DQ. So this big Q just became a little q, because unlike in the last problem, now the total charge of the object is the charge on the entire disk, whereas in the last problem, it was just the charge on the circle wire that was charged. All right, so now at this point, we can go ahead and integrate. And we're going to use this substitution and this substitution simultaneously to get rid of dq. Because in this case, you can check that as you change q, right? Like if I picked a smaller band, then my y would change. And so in that case, y would not be independent of q. Y is dependent on wherever that band of charge that you're picking is. So we can no longer pull out a bunch of these constants. Now, of course, A is a constant and Coulomb's constant is a constant. So there are things we can pull out. So using the two substitutions above, we can write that dq equals, well, let me write it, sigma times 2 pi y dy. So like rewriting that, I could maybe make it look a little nicer. 2 pi sigma y dy. Now I'll go ahead and substitute that in, pull out some constants. And of course, the integral of dE is, or the integral of 1 dE is just the total E field. So pull out the constants that I can, Coulomb's constant and A. And I'm going to pull out more constants too, but for now, we'll leave it at that. So dq was substituted instead for 2 pi times the surface charge density times y dy. And we still have the same denominator here. Okay, so we have more constants we can pull out now. We could pull out 2 and pi and sigma, because sigma is a constant in this problem. Otherwise, we'd be in real trouble. So we can pull out those things. So what we end up with is 2 pi sigma times ke times a. That's on the outside of the integral. And what I'm left with on the inside is y over a squared plus y squared to the 3/2 integrated with respect to y. So now we have it set up. That's half the problem right there, and probably the harder half because of all the kind of tricks that you either need to know or come up with on the spot. And so at this point, we're just going to look and see if we can integrate this by hand. And my first thought is, let's see if a U sub works, right? If a U sub works, great. We know how to do that. So I look in the denominator here and I see that the derivative of this term with respect to y is 2y dy, right? So in other words, this power y is 1 greater than this power, so this would make for a good U sub. So we'll go ahead and let u be defined as a squared plus y squared. And so then du would be 2y dy. And we could rearrange that to say that du over 2, right, divide both sides by 2 equals y dy. And now we have a match, right? So wherever there's a y dy, we can substitute a du over 2 because they're equivalent. And wherever there is a u, or wherever there's a squared plus y squared, we can substitute a u. And so the u substitution has done good work here. It's going to make this integral a lot easier to solve. So now E is equal to 2 pi sigma times Coulomb's constant times A. The integral of 1 over u to the 3/2, and then all that times du over 2. So that's what the sub looks afterwards. I can pull the 2 out of the integral and it'll end up canceling like this. So I'll rewrite this with a negative power to make it easier to integrate. So now I have pi sigma KEA integral of u to the minus 3/2 with respect to u. And so for now, let's just go ahead and ignore this because we're just going to have to carry it along the way. Let's just focus on this u integral real quick. So do that down here. Of course, we can use the kind of reverse power rule here. So we add 1 to the power of u, and negative 3 over 2 plus 2 over 2, which is 1, right, is minus 1/2. And then we go ahead and divide by what the power became. And we go ahead and, invert and multiply. And what we end up with is like minus 2u to the minus 1/2. And at this point, I'm going to check and make sure that I'm tracking along with my work from earlier. Okay. Yeah, this looks similar. So now I'll go back to the full equation. I'm going to pull the minus 2 out since it's a constant. So now I'm left with minus 2 pi surface charge density times Coulomb's constant times A. And then I've got this completed integral, right, that is 1 over the square root of u, which is equivalent, right? 1 over the square root of u is the same thing as u to the minus 1/2. All right, so now that I've done my u sub, I can either plug in and find new bounds for my integral in terms of u, or I could go ahead and resubstitute back in my variable y, which I'm going to do. I think I just prefer it for this problem. So we'll rewrite it again. And this time, right, 1 over the square root of u, well, u was equal to, defined as a squared plus y squared under the root. And now we have to figure out our bounds, which I really should have written up here. So we'll go ahead and do that. So like we talked about earlier, we're starting with the smallest band having radius 0. So y would be 0 at that point. And we're doing all such bands that make up this particular disk all the way up until the largest radius of the disk, which we were given as r. So the bounds here are from 0 to big R, the radius of the disk. All right, so we plug some things in and we're almost done. The solution is not a pretty one, but it's functional. It'll work. All right, so now I'm plugging in my bounds to finish the integral off, the definite integral off. And so for this first one, wherever there's a y in my this term in here, wherever there's a y, I'm going to plug in big R. And then for this next one, right, my lower bound, wherever there's a y, I'm going to plug in a 0. And I'm going to subtract that off. So now y is just 0. So leaves me with this term. And keep it going. It's a lot of stuff to write, isn't it? So at this point, what I'm going to do, I don't like this negative sign out here. So I'm going to flip my subtraction operation here, right? I'm going to flip the terms around and pull out a negative sign to cancel with this negative sign, just to make it look pretty. So doing that, we see that 1 over square root of a squared. Well, square root of a squared is just a. So we end up with 1 over a minus, then we have 1 over the square root of a squared plus big R squared, the radius of the disk squared. And finally, for the last step, to make it look like the book does, let's see here, we're going to pull out an a from the denominator of both of these terms in here. So, or actually, I'm sorry, we're going to distribute this a into both of these terms. And what that's going to leave us with is the final answer, so I should probably write it down here. E equals 2 pi sigma ke 1 minus a over square root of a squared plus big R squared. All right, so that will be what you will find in the book for this particular example problem. I hope I was able to add a little bit of insight into the tricks of this problem and into the method of setting it up. And I'll see you next video, where I will be discussing near field approximations of this disk and far field approximations, which is another way of saying, what if the point of interest is super close to the disk? What would the E field approximately be there? And what if my point of interest was way far away? What would be a good approximation there? So that's the far field approximation and the near field approximation. And we'll talk about that next video. All right, thanks for joining and have a great rest of your day.